Okay, so part 2 of the section 18 video. We've talked about the theory. Now I want to talk about the practice of how we do our actual problems. So, example. The drug 6-MP is used to treat leukemia. We have 21 patients, and for each patient we have their remission time in weeks. 21 numbers of weeks. If we take those 21 numbers and average them together, add them up, divide by 21, x bar, we get 17.1 weeks. And the standard deviation of those 21 numbers, the old section 2 standard deviation of those 21 numbers, is 10 weeks. So the remission times for 21 patients produce a sample average of 17.1 weeks and a sample standard deviation of 10.0 weeks. And here we have that symbolically. Again, notice that both x bar and s are statistics. They refer to the sample. They refer to the 21 patients. So if this were a problem from section 12 or 13, they would say assume that the standard deviation of all leukemia patients is so-and-so weeks. That would be our sigma. Here they don't say anything like that. Here all they tell us is how the 21 patients we looked at happens to vary. So this is our sigma unknown version of our procedures. The fact that this is an S rather than a sigma means we have to use the t-distribution to find our answers. We'll do a confidence interval, we'll do a hypothesis test or two. So let's organize our facts. We know the mean of the patients we looked at. We know the standard deviation of the patients we looked at. We're interested, in one sense or another, in the mean remission time for all possible patients using this drug. You can think of it as 21 patients picked from the population of all possible patients. The mu, the mean remission time for all possible patients, the ideal remission time, if you like. Neither do we know sigma, the standard deviation for all possible patients. We do not know anything about this drug in the abstract. We don't know its average remission time. We don't know how remission times vary for patients in general. All we know is how this particular 21 patients happened to play out. And we'll assume it's a simple random sample, etc., for the purposes of doing the problem. The fact that we don't know sigma makes it a t-test. So if you want a 95% confidence interval for the mean remission time for all possible patients, the ideal remission time, if you like, using this drug, then it'll play out pretty much exactly the way it did before. X bar plus or minus, supposed to be z, sigma over the square root of n. The fact that this is an S makes this a t. So fill in the blanks. X bar is 17.1. The S is 10. This is 21 down here. That confuses people. It really is n down here. The n minus 1 doesn't come into it yet. It really is still square root of n in the formula. So 21. And then we'll go to our t-chart. How does 95% confidence interval work for a sample of 21 patients? Well, again, the degrees of freedom is one less than the sample size. So on our t-chart, we'll scan down to the 20 row. Let's make that a hair smaller. On our t-chart, we'll scan down to the 20 row, one less than the sample size. And if you want a 95% confidence interval, then you look at the appropriate column. So on the 20, 21 minus 1, 20 degree of freedom row, the thing that corresponds, the thing that would otherwise be the 196, is now the 2.086. Notice how these work as you go down the columns. As, like I said, it gets closer and closer to what you would get for the z distribution. It ultimately ends up there. But this is nothing like 1,000 or 1,000,000. This is only 20, so it is substantially different from using the 1960. In particular, it's bigger. think about how this plays out. The fact that we're estimating sigma using S, this is not how the population varies. This is our only guess at how the population varies. That additional randomness introduces more uncertainty. So instead of 1960, it's 2.086. You're multiplying by it, so that in turn makes this bigger. It makes the margin of error bigger than it would otherwise be. It makes the margin of error bigger than the corresponding Z procedures, which means what we get is a little more than what it would be if it were 196, 4.55 weeks. The margin of error is a little bit bigger than it would otherwise be. So we are 95% confident that the average remission time is between these two numbers. I didn't compute them here, but you can figure it out. 17.1 minus 455, 17.1 plus 455. We're 95% confident that the average remission time for all possible patients is between those numbers. We have a 95% confidence interval for mu. We are 95% confident that the average remission time is 17.1 weeks with a margin of error of 4.55 weeks. All of our usual ways of saying it. Provided our sample is one of the 95% most typical we could have gotten, the average remission time for all patients must be between the walls. Unless our sample is among the 5% most unusual we could have gotten, the average remission time for all patients must be between the walls. As always, you can't assume anything. You're simply playing the odds. These could be the 21 quickest acting patients that this drug will ever have, or they could be the 21 slowest patients this drug will ever have. But they probably aren't. We probably did not have that weird of a sample. Provided our sample is not all that weird, 95% most typical, the truth is between the walls. If our sample happens to be one of the 5% weirdest ones, the walls are useless, but they probably aren't. That's what confidence means. On the other hand, if you want a 98% confidence interval, then instead of using the .326 that we would otherwise be using for Z, for 98% confidence, we'll use the 2.528. And, it's wider than it would be for the 95% because you're trying to be more confident. It's also wider than it would be for the corresponding 98Z interval because there's more uncertainty involved. We're estimating sigma with the 10. And that is all said here. So for confidence intervals, it works pretty much exactly the way it did before. And here's the 98 answer. Hypothesis test example. A previous leukemia drug had average remission time 21.7 weeks. What have we got? 10 weeks. So in point of fact, these patients' average time was better, faster, faster is better than the average remission time for the old drug. A previous leukemia drug had average remission time 21.7 weeks. Maybe this new drug is better, maybe it's not. But of course, better would mean a lower remission time. If nothing else, the better, as opposed to say different, should tip you off that it's a one-sided test. As always with these hypothesis tests, it's not a question of which side. That will take care of itself. It's a question of how many. So at least if you peg that the better tells you you're talking about one direction, then everything else will take care of itself. But that being said, it's nice to get it right. Better would mean a lower average remission time. So one theory is that on average, 6MP has the same average remission time as the old drug. If 6MP is exactly like the old drug in this regard, then the average remission time for all patients using 6MP will be the same as the average remission time for the old drug. If it's better, then it will have a lower remission time. the average remission time for 6-NP, if it's better, will be less than it was for the old drug. So that sets up our options. Bottom line is, it's a one-tail test. In particular, it's a left tail test, but that doesn't matter so much at this point. So we do this exactly as before. Assuming age 0, what's the probability of a sample as weird as ours? What does that mean in this case? As low as ours. Assuming that the drug works exactly the same as the old drug, how weird is it that 21 patients had an average this low, 17.1? I think I mentioned the 10 earlier, but it's the 17.1. Assuming that 6-NP works exactly the same as the old drug, how lucky is it for 10 patients to have an average remission time this low? Is the 17.1 suspiciously less than the 21.7, or is it just random chance less? If it's suspiciously less, we'll go with HA. If it's just a plain old random chance, we'll stick with H0. That's our p-value in theory. The probability of getting a sample as low as ours, assuming the drug works just like the old drug. If we really are bouncing around 21.7, how weird is it to get to bounce over to something as small as 17-ish? So we compute this exactly as before. To get the test statistic, we subtract what we are assuming to be the mean. There's our statistic, 17.1. We'll subtract what we're assuming to be the mean. Remember, we're under the umbrella of H0 being true, and divide by the standard deviation. It's supposed to be sigma over the square root of n, but what we have here is our best guess at sigma over the square root of n. The fact that it's an s makes this a t. So the s is 10. It really is the square root of n. It really is 21. Again, this is not the degrees of freedom issue. This is still the sample size down here, 21. Compute it out, and you get negative 2.108. Now, the z we rounded to 2 places because that's how it worked when we went to look up the p-value. Now we're not really looking up the p-value, so it really doesn't matter how you round it. But 3 places make sense for reasons we'll see in a second. So call it negative 2.108. Now again, the fact that it's a less than means it's a negative, but the sign is not going to matter too much here, as we'll see. As always, it's not a question so much of which tail as how many. As we've seen before, if it's a two-tail test, you double the p-value. Now we've got a bigger problem. If you don't know the p-value, you can't really double it. But we'll worry about that in a minute. We are not doubling it for this problem. It's a one-tail test. Less than, greater than, one tail. Not equal to, both tails. We're in the former situation. The logical question to ask, is it a better drug? And the question we are in point of fact asking, one directional. The degrees of freedom now is 1 less than the sample size, exactly as before. So we're still doing all of our work on the 20 degrees of freedom row. But now we're going to have to be a bit clever about how we do this. Ignore the sign on the T. As you see, all the entries in the chart are positive numbers, and filling it up with negatives would not really add anything. Notice how this plays out. For the Z procedures, it's easier just to make it negative and look it up, because the tails are on the negative side of the chart. We've talked about that shortcut. But here, putting a minus sign in front of all these numbers wouldn't add anything except clutter. So we're literally just going to ignore the sign. As you can sort of guess from the header here, it's not a question of which tail, but rather which header we're going to be looking at. We are talking about one tail. So what we'll do is we'll scan along the 20 degrees of freedom line, looking for 2.108. 2.108. Notice the way these work. As with the Z, a big-sized number cuts off a small tail. A number closer to 0 cuts off a big tail. So you can see the trend in the entries here. RT is between, what was it? It was 2.1 something. So it is between the 2086 and the 2.528. Bigger this away, smaller this away, and here's where we end up. So the corresponding one-tail p-value, just go all the way up. I can't highlight both of these at the same time, I think, at least not while holding the microphone. Nope, not going to work. RT is between 2.528 and 2.086, so our one-tail area is between 1% and 2.5%. 0.1, 0.25. And that's all summarized right here. So because RT is between the 2.528 and the 2.086, our one-tail area is between 0.25 and 0.1, between 1% and 2%. And here we are visually. So the arrow here indicates the top numbers, bigger tails. Notice that, again, the T's go in the opposite direction from the tails. A bigger T cuts off a smaller tail. So on the bottom, our T is between these two. Therefore, on the top, our p-value is between these two. And we have our answer ballparked. Assuming age 0, assuming that the drug works just like the old drug, how weird is it for 21 patients to have an average remission time this low? Well, it would occur between 1 and 2.5% of the time through random chance. And from there, you can decide whether it's suspiciously small at various levels. Notice we are ballparking this. Is the p-value less than 2%? No idea. Not with this chart. But I won't ask you questions you can't answer. It's less than 2.5%, it's less than 5%, it's less than 10%, it's not less than 1%. Of course, if it's less than 2.5%, it's less than something bigger. So here we are. And here we have it summarized. Although we can't compute the area of the tail corresponding to 2.108, notice we don't have to do so. All we have to know is whether it's too small to believe. It's enough to ballpark it, and we have ballparked it. The p-value is between 0.1 and 0.25. It would occur between 1 and 2.5% of the time through random chance. That's enough to answer any of the questions you'll be asked. We'll stick to we'll stick to the three most common levels, the 1% level, the 5% level, the 10% level. If happening less than 1% of the time through random chance makes it suspiciously unusual, then you're not there yet. The p-value is not less than 1%. Less than 1% would be over this way, and that's not where we are. Our p-value, whatever it is not less than 1%. So at the 1% level, we do not reject age 0. We have no evidence of HA. It is still plausible that the drug on average works just like the old drug. We have no evidence that it is better, that it has a lower average remission time than the old drug. On the other hand, at the 5% level, our p-value is less than 2.5%, which in turn is less than 5%. As you can see, we are on the, again, the arrow goes with the top, so we are on the small side of 5%. It is, whatever it is less than 0.5. So we will reject age 0, and we will find evidence of HA. If happening less than 5% of the time through random chance makes it suspiciously unusual, then yes, this bunch of patients is suspiciously unusual, is suspiciously good. So we will credit it to the drug. We will reject the theory that the average remission time is the same as the old drug. We will find evidence that it is got a lower remission time, that it is better. And at the 10% level, exactly the same. It's less than 10%, so we'll reject age 0. We'll find evidence of HA. At the 10% level, if happening less than 10% of the time through random chance makes it suspiciously unusual, then yes, this sample is suspiciously unusual. We'll reject the theory that the drug works the same as the old drug. We'll find evidence that it's better. Specifically, we'll reject the theory that the average remission time is the same as the old drug. We'll find evidence that it's lower. Lower remission time is better, of course. Second question. Now, of course, in this particular case, asking the two-sided question would make you a bit of a sociopath, but for the sake of argument, does 6-MP have a different average remission time from the old drug? Bookkeeper somewhere wants to know whether the 6-MP has the same remission time as the old drug or whether it simply does not have the same remission time as the old drug. Better or worse. He doesn't care whether it's better or worse. For bookkeeping purposes, he wants to know whether it's got a different average remission time than the old drug. So that changes things a bit. Now our assumption is that it's got the same average remission time as the old drug, and our HA is that it's got a average remission time that is not the number of the old drug. Plays out exactly the same as before. Assuming H0, what's the probability of getting a sample as extreme as ours? Only now you mean as far from the center as ours is. Assuming that 6-MP works the same as the old drug on average, how weird is it for 21 patients to get an average remission time as far away from 21.7 as 17.1 is? Both tails. Bottom line, everything goes through exactly as before, 2108, degrees of freedom 20. Ballpark it, it's exactly where it was before. But now we're looking at the two-tail header. The two-tail p-value is between 2% and 5%. Our t is between, t of 2.1 something is between the 2528 and the 2086, exactly as we were before, but now we're looking at the two-tail header. Notice that the two-tail header is not strictly necessary. All it does is double the header directly above. But nevertheless, it saves you the work, so it's nice to have it. The two-tail area, our current p-value, our two-tail p-value, the area of both tails, the probability of getting a sample as far away from 21.7 as ours is, well, it's between 2% and 5%, 0.205. It's not enough to change any of our answers in this case, but it is a little bigger than it was. It does change our logic a bit. Before it was explicitly more than 1% and kind of implicitly less than 5 and 10 because it was less than something smaller. Try again. It was explicitly greater than 1% and implicitly less than 5 and 10 because it was less than something which was in turn less. It changes your logic a bit here, but it doesn't really change where it falls in relation to the 1 and the 5 and the 10. Yeah, it's a little bigger than it was, but it's still more than 1%, still less than 5 and 10%. So it changes the logic of your situation. As usual, if you double something, it's bigger than it was, so it's harder to reject the H0, but it could change your answers in theory. In this case, it doesn't. At the 1% level, our p-value is bigger than something which is in turn bigger than 1%. So as you can see, again, the arrow refers to the top. It is not on the small side of 1%. It is on the small side of 5 and 10%. So at the 1% level, no, our p-value, whatever it is not less than 0.1. So we're not going to reject H0. We're not going to find evidence of HA. Changes our logic, our conclusions a little bit. We are not rejecting the theory that the average remission time is the same as the old drug. We are not finding evidence that the average remission time is different. Not low, not high, not better, not worse, different. There's no evidence that the average remission time is different from the old drug. On the other hand, at the 5 and 10% levels, yes, we are less than 5%. We are less, if you're talking about the 10% level, then we're less than something which is in turn less than 10%. Bottom line, it is less than the 5 and 10% levels. So if you've got to occur less than 1% of the time through random chance to be suspiciously unusual, we're not there yet. But if your standard is that you've got to occur less than 5% of the time through random chance, or 10% of the time through random chance, to be suspiciously unusual, then yes, it is that suspiciously unusual. Again, it's explicitly less than 5%, and it's implicitly less than 10% because it's less than something that's less than 10%. But bottom line, it is on the small side of the 5 and 10, so we will reject at those levels. At the 5% level, at the 10% level, yes, we'll reject the theory that the average remission time is the same as the old drug. Yes, we will find evidence of HA that the average remission time is purely different from the old drug, not the same. So there's some confidence intervals and hypothesis tests for the section 18 sigma unknown problems. Remember, these are very similar to the 12 and 13 ones, except if you don't know the sigma, you've got to use the t-chart. For confidence intervals, not that big a deal. For hypothesis tests, we have to ballpark the value. Section 19 will continue on in a very similar way. It's going to be using these t-charts again. The problems will be very, very similar. A bit more of a prologue, but when you get up and running, it's pretty much exactly what we're doing now. I'll show you how that works in the next video.